morning, students. In the last session, we were discussing about atom molecules and the valency. Now, today we are going to proceed forward with another topic of atomic mass. So, normally when we talk about the whole atom itself, we write the structure of the atom in this kind of format over here. Is that clear? So, there are three different kind of like subatomic particles, that is proton, neutron, and electron. Since proton, they are positively charged, we used to write positive here, and neutron, this is negative, neutral charge, which is why I write 0, and then in the case of electron, this is negatively charged here. So now why I write positive over here is because proton and neutron, they are present in the center, since neutron doesn't carry any kind of charge, which is why we are writing proton as positively charged here. Okay, so now this electron, they used to revolve over here. Now, whenever we talk about atomic mass, it is very important for us to know that there are three different subatomic particles in atom. But when you talk about electron here, this electron, it doesn't matter, okay, how many amounts of electrons are present. But the point is, these electrons, they have a mass negligible to that of our 0 here. Is that clear? So, which is why we never used to consider the mass of the electron when we are measuring the atomic masses of the atom. Is that clear? So, there are three subatomic particles, but we never used to consider electron. Why? Because electron mass is somewhat negligible to 0 here. Is that clear? So now, this proton, they carry some mass, whereas neutron, they also carry some mass. But neutron doesn't carry any charge. Keep that in your mind. Is that clear? So, whenever we come across atomic mass here, atomic mass, what is important for us to know is that whenever we are calculating atomic mass, you have to sum up or you have to add up the number of proton, that is the number of proton plus the number of neutron. When you do that, when you add up the number of proton plus number of neutron, you get the value of atomic mass. Is that clear? For example, let us take an example in the case of sodium here. Sodium is atomic number 11, and sodium has the number of proton as 11, whereas sodium has the number of neutron as 12. Now 11 plus 12 is how much? This is equal to 23. That is the atomic mass of the sodium. Is that clear? Okay. Do you understand this? So now let us proceed forward with another kind of step for back here. Is that clear? Okay. Okay. Molecular mass here. So I'm going to write a fictional diagram of a donkey here. Okay? So now let's say this is a donkey. And I guess many of you have heard the story of donkey carrying some amount of wool. Okay? Let's say this is a wool. Okay? And this donkey was somehow faking it, that this wool was particularly very heavy. Now when he was crossing a water from this zone to that zone over here, what we will come to know is that the donkey on this side, let's say, this is the wool. Okay. Now at that side, the total mass of this donkey somehow, let's say, is 10 kg. Let's suppose, man, this is 10 kg. Now, do you really think that the moment this donkey is going to cross this river, is it still 10 kg over here? That's not the case here, right? It is going to become much more heavier here. Why? Because this wool is going to absorb all the water on that. So we will somehow come across like 20 kg here. That means it has become much more heavier. Why it has become heavier? Because over here, there is the presence of donkey, the animal itself, plus wool, plus water. That is the water. So whenever we are finding out the mass, so what we used to do is that we used to sum up all the like elements, like all the materials which are present on that particular object itself, right? So now let us talk about molecules. In the previous classes, I guess every one of you must be having some brief idea about what is molecules. When two or more atoms, they combine together. When they combine together, they form molecule. Is that clear? This is the molecule. Now, I'm going to write a very simple molecule over here. Simple molecule. That simple molecule is something which we are used to it. That is water molecule. Is that clear? Now, try to think about that particular kind of analogy which I have used previously regarding the donkey, wool and the water. Now in this case here, you can find how many atoms in that. I guess you will find three kind of atoms here. How? There are two hydrogen and one oxygen here. Is that clear? So what we used to do is that normally the mass of the hydrogen, that is one hydrogen atom, is 1 here. Is that clear? But since I have written 2 over here, so I have to multiply that by 2. Is that clear? Now, this hydrogen atom and this oxygen atom are totally different, so I have to write plus here. Understand? And the mass of the oxygen is 16. So, summing up these two, what I will get? I will get 18 mu here. And this particular mass is what we used to call as molecular mass. Is that clear? Even we take the example of carbon monoxide here. These two are totally different elements here. Carbon is having an atomic mass of 12 plus oxygen is having an atomic mass of 16. So when you sum up all of this, what you will get is 28 mu. Is that clear? So generally when we talk about molecular mass, means it is the total mass of all the atoms present in the molecule. This is what we used to define as molecular mass. Is that clear? Now there is a slight change. Okay, slight change here. There are two different kind of modes here. One is I'm going to write this out. One is like relative molecular mass. Relative molecular mass. And another one I will write in the next one. Now, regarding the relative molecular mass, it is the same thing which I have written just now, that is the molecular mass itself. But when we talk about the word relative, we are comparing it with something else. That is, regarding the relative atomic mass, we did compare the mass of the atom with that of carbon-12 isotopes here. Is that clear? So now, I don't want to make this very confusing by breaking up so many different kinds of relative atomic mass, though we had learned in the previous classes also, right? Now, let's suppose imagine, okay, there is carbon monoxide here. Okay? This carbon monoxide, they are normally independently existing. They used to independent existence. They used to exist independently. And when we were supposed to find this molecular mass of this carbon monoxide, as I had done previously, carbon is like 12 and oxygen is like 16. When you sum up these two, you get 18, that is, 28 mu. This is what we got. Understand? But there are some other elements like NaCl. Let us think about this one. That is the common salt, NaCl. Let us think about this particular one here, NaCl. Now this NaCl, first thing here, it doesn't exist independently. Is that clear? It doesn't exist independently. I'm going to write here. It doesn't exist independently. Secondly, in the case of NaCl here, as you can see here, NaCl, you can find two different kind of ions here. That is, in the case of NaCl, what we can conclude here is there is a presence of Na plus and there is a presence of Cl minus. I hope I don't have to repeat that once again, because we have discussed this particular topic in the ions chapter itself, right? Okay, so now here, NaCl, you write here, NaCl. Na plus, Cl minus. Now sodium is, atomic number is 11, which is why we can write the contribution as 2, 8 and 1. That means 2 plus 8 is 10 plus 1 is 11 here. Now in the case of chlorine, atomic number is 17, which is why we write 2, 8, 7 here. Is that clear? Now in the third shell, there is a presence of like 8 electron. There should be a, a space for, a vacuum space for 8 electron. But over here, I can find only 1 electron over here. So it has become a very difficult task for me to bring 7 more electrons over here. So instead of bringing 7 more electrons, what I can do is that I can remove this 1 electron. Is that clear? So when I remove this 1 electron, it goes to chlorine. Now in the chlorine, this third shell, they have space for 8 electrons, and I'm going to add 1 here. This is going to become 8 here. Is that clear? So now in the sodium, number of proton is almost like 11, but number of electrons became something like 10. Clear? Now over here, the number of proton is 17. But the number of electron, now count 10 plus 8 is 18. Is that clear? So now positive and negative is, which one is more in number? Positive is more in number by how much? 1, which is why we are writing Na plus 1. Whether we write 1 or not, it doesn't make any kind of difference here. Now in the case of chlorine here, there are like, see the difference between these two. Negative is more in number by how much? 1, which is why we are writing this minus 1 here. But I'm not writing 1, it doesn't make any kind of difference. So when you find any kind of molecules which are not existing independently, and secondly, they are made up of ions, we call the molecular mass of these kind of like molecules as formula unit mass. Is that clear? There is a slight difference in the usage of the term. Formula unit mass. Is that clear? Relative molecular mass and formula unit mass, they somehow have the same kind of values. But are they different? Yes. How they are different? In the usage of the both. Relative molecular mass, these are used on those kind of molecules which are not ionic by nature and they are existing independently. But whereas in the case of formula unit mass, these kind of like formula unit mass are used on those kind of molecules which have the presence of ions here, that is plus and minus here. And it is used on those kind of molecules which doesn't exist independently. Is that clear? And again, on formula unit mass, I will add one more thing here. Let's say this is the sodium chloride, NaCl. Okay? Now, this NaCl, let's say this is NaCl. Okay, I'm going to write roughly. Okay. Let's have a quick write this. Na plus, Cl minus. Okay, for all this, Na plus. Okay, Have a look. Now you can see this is positive, negative, and between these two positive and negative, there are some kind of like attractive forces. Is that clear? There are some kind of attractive forces. Now, in the case of ionic compound here, ionic compound means those compounds which has the presence of the positive ion, which we used to call as cation, and then this is called negative ion, which we used to call as anion. So this is a small volume here, In that small volume, so many amount of ions are stacked together. These kind of like compound is what we used to call as ionic compound, and generally formula unit mass is used for ionic compound. We never used to call relative molecular mass on ionic compounds. That is the biggest difference between the relative molecular mass and the formula unit mass. Is that clear? So I hope you all have a clear understanding regarding the atomic mass, relative molecular mass, and the formula unit mass. Is that clear? For example, now I will just give you one example, then I will just wind up. Okay? Let's suppose imagine this is water here. Okay? Now this water, if you try to find the relative molecular mass of water, this is coming out to be like the mass of hydrogen is 1 into 2 plus oxygen is 16. This is coming out to be 18 mu. Understand? And if you are asked to find the the formula unit mass of this particular compound over here, that is the molecule over here, is again 1 into 2 plus 16, that is 18 mu. So you might feel that both of them are getting the same kind of value. This is same. No, this is not the same. Formula unit mass is normally used for those kind of compounds which doesn't exist independently, and they are made up of ionic compounds. Is that clear? So this is the primary concept behind the relative molecular mass and the formula unit mass. So I hope you have understood. Thank you for listening so well. Thank you everyone. Hello everyone. So in the last session we did talk about the molecular mass, relative molecular mass, and formula unit mass. So now today we are going to end this chapter with the topic mole concept here. So the name itself, mole, it was first introduced by this particular mole. There is a scientist, his name is Oswald. He coined the word mole, which actually means heap or pile. Is that clear? Heap or pile means a pile of stones, we used to say, or we used to say heap of stones. Now, how we are going to understand this particular concept is like this here. For example, when you go to a market, you used to buy all different sorts of things. For example, you used to buy rice and you buy milk. Then you also buy, let's say, banana, right? Okay. So when you buy rice, you ask the shopkeeper that, can you please give me 1 kilogram of rice? Is that clear? So in that case here, we are measuring like kilogram here, kilogram. And when you think about the milk, we normally talk in terms of liter here, liter. Now in the case of banana here, we say, give me a dozen of banana, or you say in terms of eggs and everything, dozen means 12, right? So we have these different kind of measuring units here, that's kilogram, liter, or dozen. We have these measuring units which we use in our daily life. But what if the items or the things which we are going to measure, they come in the form of very small tiny particles? What if they come in the form of tiny particles? Tiny particles. Tiny particles. Like atom. Like atom. So now, in the case of measuring atom, can we still use kilogram? Can we use liter? Can we use dozen? I don't think that's possible for us to use kilogram, liter, and dozen. So this is how this particular mole was introduced here, to measure So in a way, you can say what is mole? Mole means mole is a way of measuring the unit by which we can measure the small tiny particles like atom. Is that clear? Let's go for it. Okay. So let's say now this is atom here. This atom, or let's say molecules, or let's say ionic particles. There is a guy, his name is called Avogadro. His name is Avogadro. He has researched and he gave a particular kind of conclusion that one mole of any species, is equal to 6.022 into 10 raised to power 23. Now this is a number. This number was somehow given by Immediate Avogadro, which is why this number is also referred to as Avogadro number. Is that clear? Now let's talk about let's say helium here. Helium. If I say 1 mole of helium, we can somehow conclude that in that particular 1 mole there is 6.022 into 10 raised to power 23 helium atom. Is that clear? So now, keeping all of this in our mind, what we need to understand is that 1 mole of any species is equal to 6.022 into 10 raised to power 23 number. Is that clear? So now look at this particular species here. You must be thinking, what is that species? Right? Okay, so normally when I talk about this particular kind of species, I mean 3 things here. Is that clear? Number 1, if we are talking in terms of element here, we use that particular species. Instead of using that particular species, we use atom here. Okay? And secondly, when we talk in terms of molecules here, we use the word molecules here. 1 mole of oxygen molecule, 1 mole of water molecules. Right? Number 3, we talk in terms of ionic compounds, which could be ions here. Is that clear? So now in short, if I conclude here, what I'm going to say is that 1 mole, generally 1 mole is equal to 6.022 into 10 raised to power 23. That number is present. Now it's okay if you go to a supermarket and you can say something like, can you please give me 1 mole of chocolate? You are not wrong in that. But if you ask the particular store owner that I need 1 mole of chocolates, that means you are asking for 6.022 this number of chocolates. Is it possible for us to is it possible for the store owner to produce this much amount of chocolates to you? I don't think it's possible. That is why we don't use this mole in our daily life. So this particular mole concept is normally used by the chemist here. Is that clear? So now 1 mole is equal to 6.022 into 10 raised to power 23. That is a number. But 1 mole of what? The 1 mole of, it could be atom, it could be molecule, it could be ions also. Is that clear? So I have written the scientific definition of mole over here. That is the amount of substance that contain the same number of atom, molecules or particles, could be ions there, as there are atom in carbon-12 isotope here. Carbon-12 isotope. So if you find this as very confusing here, let me just tell you one thing here. That this is the part here. Same number of atom, molecules or particles, right here. This particular thing here, same number of atom, molecule or particle is equal to the same number of atom in carbon-12 isotope here, 12 gram of carbon-12 isotopes. How we are going to do that? Let us do that, okay? Okay, so this is the formula which I normally used to write in the case of mole concept here. Sorry. Okay, this is n into, right? I'm sorry, this is, I'll write something like this. Okay, this n signifies number of moles, okay, and this m signifies given mass, and this m signifies molar mass or molecular mass here. Now let us try go for it. Carbon 12 gram of carbon 12. Let us go for it. Have a look. 12 gram of carbon 12. That means I'm going to write the formula here once again. Okay? Here. They have given, that is n is equal to given mass. Given mass of 12 gram here. 12. I'm going to write. And this is the number of moles. And the molar mass, that means what is the mass of the carbon 12? Carbon 12 mass is carbon. Carbon has 6 proton plus 6 neutron, that is equal to 12. That is the mass of the carbon, which we are going to write 12 like this here. And when you cancel this, what value you will get? N is equal to 1 mole. 1 mole, I'm sorry, 1 mole. Is that clear? So whenever we are using 12 gram of carbon 12, we are getting 1 mole. Is that clear? Now let us imagine, okay, if I say 2 mole of helium. If I say 2 mole of helium, that means I have to multiply 2 into 6.022 into 10 raised to power 23. That much number of helium atom is present. If I say 3 mole, you have to multiply by 3. Is that clear? This particular concept was first brought forward by Avogadro, and this particular number, that is 6.022 into 10 raised to power 23, is what we refer to as Avogadro number. Is that clear? And this formula is very, very helpful for you in understanding, in finding out the number of moles and the given mass of that particular compound here. Is that clear? For example, let's say if they gave you like 24 gram of carbon 12, how many moles are present in that? Once again, we are going to write the triangle part here, and they have given the value, that is given mass is equal to 24, and number of moles is m, and carbon 12 molar mass is how much is that? 12. When you cancel this, number of moles is equal to 2 moles. If you are going to find for this, we are going to multiply this 2. Is that clear? So this is how we find and how we use this particular concept in measuring the number of moles. Is that clear? In measuring the subatomic particles like atom. And normally this concept is primarily used by the chemist people, the people who used to mingle or who used to indulge in all these kind of subatomic particles. We used to call these people as chemists, and this concept is very helpful for them. Is that clear? So thank you very much, all of you. So I shall see every one of you in the next session, and I'm going to start with the structure of atom. Thank you very much, all of you.